Hello and welcome. In this video, we will explore the fundamental operations with plane vectors, a key topic in the IB mathematics analysis and approaches higher level curriculum. By the end of this session, you will be able to perform algebraic vector addition, subtraction, and scalar multiplication, and you will be able to solve problems involving these operations. We'll start by reviewing the concept of vector magnitude, which is essential for understanding unit vectors and solving related problems. First, let's recall how to find the magnitude of a vector. The magnitude represents the length of the vector. For a two-dimensional vector, let's say vector v, with components v1 and v2, its magnitude, denoted by the absolute value bars, is calculated using the Pythagorean theorem. This is because the components v1 and v2 form the legs of a right-angled triangle, and the vector itself is the hypotenuse. The magnitude is simply the length of that hypotenuse. Let's work through an example. Consider the vector v equals the column vector 3, 4. Using our formula, the magnitude of v is the square root of 3 squared plus 4 squared. This simplifies to the square root of 9 plus 16, which is the square root of 25. The magnitude of vector v is 5. So the vector 3, 4 has a length of 5 units. This process is fundamental for many vector calculations. Now let's apply this to a slightly more complex problem. We're given a vector v with components 8 and p, and we know its magnitude is the square root of 73. Our goal is to find the possible values of p. Here's the problem statement. Given vector v equals 8, p, and its magnitude is the square root of 73, find p. We'll start with our magnitude formula and substitute the given information. The magnitude of v is the square root of 8 squared plus p squared. We are told this is equal to the square root of 73. To solve for p, we can square both sides of the equation to eliminate the square roots. Squaring both sides gives us 8 squared plus p squared equals 73. 8 squared is 64, so we have 64 plus p squared equals 73. Subtracting 64 from both sides, we find that p squared equals 9. Finally, taking the square root of both sides, we get p equals plus or minus 3. It's crucial to remember both the positive and negative solutions here. This means there are two possible vectors, 8, 3, and 8 minus 3, that have a magnitude of the square root of 73. This demonstrates how the magnitude formula can be used to find unknown components. Next, let's define a special type of vector called a unit vector. This concept is very important in physics and engineering. A unit vector is simply a vector that has a magnitude of exactly 1. Its purpose is to indicate a direction without specifying a length. To check if a vector is a unit vector, we just need to calculate its magnitude and see if it equals 1. Let's test the vector v equals the column vector 0, minus 1. The magnitude of v is the square root of 0 squared plus negative 1 squared. This simplifies to the square root of 1, which is 1. Since the magnitude is 1, yes, v is a unit vector. Now, let's try another one. Consider the vector w equals the column vector 2/3, 1/3. Is w a unit vector? The magnitude of w is the square root of 2/3 squared plus 1/3 squared. This is the square root of 4/9 plus 1/9, which is the square root of 5/9. This is not equal to 1, so w is not a unit vector. This process of checking the magnitude is the standard way to determine if a vector is a unit vector. What if we have a vector that isn't a unit vector, but we want one that points in the same direction? We can create a unit vector from any non-zero vector. The formula is straightforward. The unit vector in the direction of v, often written as v hat, is the vector v divided by its own magnitude. This process is called normalization. It scales the vector down to a length of 1 while preserving its direction. Let's find the unit vector in the direction of v equals 3, 4. First, we need the magnitude of v. We already calculated this in a previous example. The magnitude of v is the square root of 3 squared plus 4 squared, which is 5. Now we apply the formula. The unit vector v hat is the vector 3, 4 divided by its magnitude, 5. This gives us the unit vector 3/5, 4/5. This vector has a length of 1 and points in the same direction as the original vector, 3, 4. This technique of normalization is a powerful tool for working with vectors. allowing us to separate a vector's direction from its magnitude. Now let's move on to the operations themselves, starting with vector addition. We'll look at both the geometric and algebraic interpretations. Geometrically, we use the Hoare head-to-tail rule. To add vector A and vector B, we place the tail of vector B at the head of vector A. The resultant vector, A plus B, is the vector from the tail of A to the head of B. This rule is intuitive. It represents the combined displacement of moving along vector A and then along vector B. Algebraically, addition is much simpler. If vector A has components A1, A2, and vector B has components B1, B2, their sum is found by adding the corresponding components. The horizontal components add together, and the vertical components add together. This is a direct consequence of the head-to-tail rule. Let's see this in action. Let P be the vector 3, minus 2, and R be the vector minus 2, minus 5. We want to find P plus R. We add the x components, 3 plus negative 2, and we add the y components, negative 2 plus negative 5. This gives us the resultant vector 1, minus 7. Vector addition is a straightforward component-wise operation. Now let's tackle vector subtraction. The key idea here is to convert subtraction into addition. First, we need to understand the negative of a vector. If vector A points in a certain direction, the vector negative A has the same magnitude but points in the exact opposite direction. Algebraically, you simply negate each component. For example, if A is 2, 3, then negative A is minus 2, minus 3. With this in mind, we can define vector subtraction. To subtract vector B from vector A, we add the negative of vector B to vector A. So, A minus B is the same as A plus negative B. Algebraically, this means we subtract the corresponding components. The x component of the result is A1 minus B1, and the y component is A2 minus B2. Let's try an example. Given P equals 3, minus 2, and Q equals 1, 4, find Q minus P. We subtract the components of P from the components of Q. The x component is 1 minus 3, and the y component is 4 minus negative 2. This gives us the vector minus 2, 6. Remember that vector subtraction is not commutative. Q minus P is not the same as P minus Q. The final operation we'll cover is scalar multiplication. A scalar is just a number, as opposed to a vector. Geometrically, multiplying a vector by a positive scalar k scales its length by a factor of k. If k is negative, it also reverses the vector's direction. For example, 2a is a vector twice as long as a, pointing in the same direction. Negative 1.5a is a vector 1.5 times as long as a, pointing in the opposite direction. Algebraically, scalar multiplication is very simple. To multiply a vector by a scalar k, you multiply each component of the vector by k. Let's look at an example. Given q equals 2 minus 3, find 3q. We multiply both the x component and the y component by 3. So 3 times 2 is 6, and 3 times minus 3 is minus 9. The result is the vector 6 minus 9. This operation allows us to change the magnitude of a vector while keeping its direction, or to reverse its direction. Often, you'll need to combine these operations in a single problem. Let's work through a more complex example. We are given 3 vectors, p equals 1, 5, q equals minus 2, 4, and r equals minus 3, minus 1. We need to find the vector 2, p minus q plus 1/3 r. We'll solve this step by step, following the order of operations. First, let's calculate 2p. We multiply each component of p by 2. This gives us the vector 2, 10. Next, let's calculate 1/3 r. We multiply each component of r by 1/3. This gives us the vector minus 1, minus 1/3. Now we can substitute these results back into the original expression. Our expression becomes the vector 2, 10, minus the vector minus 2, 4, plus the vector minus 1, minus 1/3. We can perform the subtraction and addition component-wise. For the x component, we have 2 minus negative 2 plus negative 1. For the y component, we have 10 minus 4 plus negative 1/3. Combining these, our final answer is the vector 3, 17/3. This example shows how to systematically combine scalar multiplication, subtraction, and addition. Let's look at another type of problem. Finding an unknown scalar k in a vector equation. We are given the equation, the vector 2 minus 5 plus k times the vector 3 minus 1 equals the vector 20 minus 11. We need to find the value of the scalar k. The strategy here is to perform the operations on the left side of the equation and then equate the corresponding components. First, we distribute the scalar k. This gives us the vector 3k dash k. Now we add the two vectors on the left side. The x component is 2 plus 3k, and the y component is minus 5 minus k. We now have a single vector on the left side that must be equal to the vector on the right side. For two vectors to be equal, their corresponding components must be equal. This gives us a system of two equations. The x components give us 2 plus 3k equals 20. The y components give us minus 5 minus k equals minus 11. We can solve either of these equations for k. Let's use the first one. Subtracting 2 from both sides gives 3k equals 18. Dividing by 3, we find that k equals 6. It's good practice to check this with the second equation to ensure consistency. Substituting k equals 6 into the second equation, we get minus 5 minus 6 equals minus 11, which is true. So our value of k is correct. Let's try another example of finding an unknown scalar, this time with fractions. We need to find k such that 1/3 times the vector minus 1, k, plus 4/3 times the vector 7, k plus 1, equals the vector 9, minus 1. Again, we'll simplify the left side first. Distributing the scalars, we get the vector minus 1/3, k, slash 3, plus the vector 28/3, 4k, slash 3, plus 4/3. Now, we add the corresponding components. The x component is minus 1/3 plus 28/3, and the y component is k slash 3 plus 4, k slash 3 plus 4/3. Simplifying the x component, we get 27/3, which is 9. Simplifying the y component, we get 5k slash 3 plus 4/3. Now we equate the components. The x components give 9 equals 9, which is true but doesn't help us find k. The y components give 5k plus 3 plus 4 divided by 3 equals minus 1. We can solve this linear equation for k. Subtracting 4/3 from both sides, we get 5k slash 3 equals minus 7/3. Multiplying by 3, we get 5k equals minus 7. Finally, dividing by 5, we find that k equals minus 7/5. This example shows that even with fractions and more complex expressions, the method of simplifying and equating components remains the same. Let's conclude with a conceptual question that reinforces the properties of vector addition. We are given two vectors, p equals 1, 1, and q equals 2, minus 1. We need to find the resultant vector for three different combinations of these vectors. Let's analyze the first expression. The expression p plus q plus q plus q can be written more compactly as 2p plus 3q. Calculating this, we get 2 times the vector 1, 1, plus 3 times the vector 2, minus 1. This simplifies to the vector 2, 2, plus the vector 6, minus 3, which equals the vector 8, minus 1. Now let's look at the second expression. The expression p plus q plus p plus q plus q can also be grouped as 2p plus 3q. Since it's the same expression, the result is the same, the vector 8 minus 1. And finally, the third expression. The expression q plus p plus q plus p plus q can also be grouped as 2p plus 3q. Again, the result is the vector 8 minus 1. The question asks us to comment on these results. The key takeaway is that the order in which you add vectors does not change the final resultant vector. This is known as the commutative property of vector addition. It's a fundamental property that simplifies many vector problems. Let's quickly recap what we've covered. We started with the magnitude of a vector, which is its length, calculated using the Pythagorean theorem. We then defined a unit vector as a vector with a magnitude of 1, and we learned how to normalize any vector to create a unit vector in the same direction. Finally, we explored the algebraic operations of vector addition, subtraction, and scalar multiplication, which are all performed component-wise. You are now equipped to perform these fundamental operations and solve problems involving them. To solidify your understanding, here are some practice questions in the style of the IB exam. Here's your first practice question. Pause the video and try to solve it on your own. Question 1. Given vectors a equals 2 minus 3 and b equals minus 1, 4, find the magnitude of the vector 3a minus 2b. Let's go through the solution. First, we need to find the vector 3a minus 2b. We calculate 3a as 6, minus 9, and 2b as minus 2, 8. Subtracting these gives us the vector 8 minus 17. Now we find the magnitude of this resultant vector is the square root of 8 squared plus negative 17 squared, which is the square root of 64 plus 289, or the square root of 353. Here is your second practice question. Pause the video and try to solve it. Question 2. A vector v has components x and 2x. If its magnitude is 5, find the possible values of x. Let's go through the solution. We'll use the magnitude formula. The magnitude of v is the square root of x squared plus 2x squared. We are given that this equals 5. Squaring both sides and simplifying, we get x squared plus 4x squared equals 25, which means 5x squared equals 25. Dividing by 5, we find x squared equals 5. Therefore, x equals plus or minus the square root of 5. Here's your third practice question. Pause the video and try to solve it. Question 3. Find the unit vector in the direction of the vector w equals minus 6, 8. Let's go through the solution. First, we need the magnitude of w. The magnitude of w is the square root of negative 6 squared plus 8 squared, which is the square root of 36 plus 64, or the square root of 100, which is 10. Now, we divide the vector w by its magnitude. The unit vector w hat is the vector minus 6, 8, divided by 10. This gives us the unit vector minus 3/5, 4/5. Here is your fourth practice question. Pause the video and try to solve it. Question 4. Given vectors u equals 1, 2, and v equals 3, minus 1, find the scalar k such that the vector u plus kv is parallel to the x-axis. Let's go through the solution. A vector parallel to the x-axis has a y-component of 0. First, let's find the vector u plus kv. This is the vector 1 plus 3k, 2 minus k. For this vector to be parallel to the x-axis, its y-component must be 0, so we set 2 minus k equal to 0. Solving for k, we find that k equals 2. Here is your fifth and final practice question. Pause the video and try to solve it. Question 5. Find the scalar k such that the vector 2, 5 plus k times the vector minus 1, 3 has a magnitude of 13. Let's go through the solution. First, we find the resultant vector. The vector is 2 minus k, 5 plus 3k. We are given that its magnitude is 13. So the square root of 2 minus k squared plus 5 plus 3k squared equals 13. Squaring both sides and expanding, we get 4 minus 4k plus k squared, plus 25 plus 30k plus 9k squared, equals 169. Combining like terms, we get the quadratic equation 10k squared plus 26k minus 140 equals 0. Dividing by 2, we have 5k squared plus 13k minus 70 equals 0. Using the quadratic formula, we find two possible values for k equals 2, and k equals negative 7. That concludes our lesson on operations with plane vectors. We've covered the essential algebraic techniques for addition, subtraction, and scalar multiplication, and we've seen how to apply these to solve various problems, including those involving magnitude and unit vectors. Mastering these fundamental operations is crucial for your success in the IB Mathematics AAHL course. Keep practicing, and you'll build the confidence and skills needed to tackle more advanced vector concepts. Thank you for watching.